Good evening, everyone, and welcome to the Vacuum Transport Seminar. This is our fourth session this semester tonight, and we welcome all of you, everyone of the audience, and as well as our two speakers today. So we will have two interesting talks today. The first one comes from the side of mu0 Hyperloop. It will be Justus Wolf, who talks about the analysis of the potential for using existing rail and highway routes in Europe for high-speed transportation. And afterwards, we will be having a talk from TUM Hyperloop side from Joris Barenze, and he will speak about the permeability measurement on concrete for Hyperloop tubes. Again, as a short reminder, we will use the slido.com website where you, the audience, can put your questions, and then after every presentation, we will have a short discussion round and a question round. Now, I would first like to hand over to Pia from mu0 Hyperloop, and yes, for that you can give a more detailed and short introduction for our first speaker. Thank you.
Sure, thank you, Natalie. Okay, so Justus, thank you first of all for taking your time and presenting your bachelor thesis to us today. Before you start, I just want to give you a really short introduction. Justus joined our association last September and joined the division C-Cubed. And amongst other things, they are doing a bit of research also on the social aspects on Hyperloop and are writing a paper for the HW on it. And furthermore, Justus is also writing his bachelor thesis with us, which he's also going to present today. It's about how Hyperloop rail, or like how existing railways can be used for Hyperloop. And I think it's a really interesting topic, and I'm really looking forward to your presentation, Justus. And with this, I think the stage is yours.
Thank you very much. All right, now I just need to share my screen. We are not using Zoom at the KIT, so I might be not as professional as other people with it. So, do you see a slide? Awesome. All right. So, thanks again for having me. I'm going to talk about the the potential of using existing rail and highway routes throughout Europe. Just a little short information about me. I'm studying industrial engineering at the KIT in the 8th semester, and now still writing my bachelor thesis, so it's not finished, but I'm going to present what I did so far. All right. So when we are talking about Hyperloops, we want to connect big cities, basically, and the optimal track is straight. That's probably obvious, but it's not as simple as it sounds. So when we have a straight track, the normal acceleration, so it's the acceleration not to your x-axis, basically, is 0, but yeah, we can't have the straight path. And the straight path is obviously the shortest path, so you want to reduce the length of your route, but it needs to be built, and we are still in Europe, and this results in these problems. So as you can see, these are just some snapshots from German press articles, and as you might remember, the upper left is from the Hambacher Forst, a big forest in Germany that, where they wanted to build an autobahn, and there were quite some protests, and it all got delayed. Or you have some animals or species that got discovered, and then you have to delay your buildings as well, or your construction, or people just file lawsuits. So if you want to conclude these articles into some points, what happens when you're building a new route is that landowners are probably expropriated from their property because you want to build your route through it, and they may file lawsuits against this idea or the concept. So you can't really build as fast as possible. I mean, if you're probably in China or other countries where the people can't file lawsuits that easily, it probably works. But in Europe, or especially in Germany, it takes quite some time. You have unknown species that you probably need to repopulate, or you have protests against deforestation, construction of roads, etc. So what we did, we were thinking, why don't we just use existing routes? So they are already built, they are owned by the government, and we can just construct or build the Hyperloop track next to the existing railway. We don't need to expropriate anyone. The probability of a newly discovered species is quite low. And but one big disadvantage is that these routes are not designed for high speeds. So the idea was to optimize the acceleration profile and then compare it to conventional trains. And so we decided to optimize our acceleration and have decided to do it with basically 3 objectives. So we minimize the travel time. That's probably the most obvious thing. But if we also minimize the comfort or maximize the comfort, this reduces our velocity, because the lower we drive, the more comfort we have, and the faster we are, the more energy the Hyperloop consumes. So we have a multi-criteria optimization resulting in this problem. So we want to minimize travel time, comfort, and energy consumption, and have some constraints on this problem. Yeah, our decision variable, I forgot it here, is the acceleration, but I'm gonna talk about that soon. So the velocity at 0 has to be 0 meters per second, and at the end we want to be at the end station. Basically, we want to be at 0 again. So then we have an upper limit on the velocity at 280 meters per second. I think that's 1080 kilometers per hour, and then we constrain the tangential and normal acceleration as well. We are currently optimizing only over travel time and comfort, and just building the sum of both with a weight. And we have, well, I haven't modeled energy consumption yet, but as I said, I'm not finished yet with my bachelor thesis, and that's going to come. I'm going to rely on some research another museum member does. And we're going to talk about it within the next days. All right. So to optimize this problem, or to solve this problem, we had to get data first, and we got the data from OpenStreetMaps, where we get the longitude, latitude, and we get the longitude and latitude from OpenStreetMap with the start and end station. But then we had to add the elevation data and then converted it into Earth-centered, Earth-fixed coordinate, basically meaning we have X, Y, Z in meters, so we can optimize over meters, and have an easier coordinate system. All right, so now I'm just talking about Hamburg, Berlin. So as I'm from Hamburg, and Berlin is probably quite a nice city, I wanted to talk about this route just to give an example. And so the question is, how fast could a Hyperloop be on this route? The route length is 270 kilometers, and you can see it below. So that's the route from Hamburg to Berlin. Yeah, Wikipedia has another route length, but that's the one we calculated. I don't know how they did it, or who did it. Yeah. So what we did is we got the XYZ data, and I'm only showing XY plots here. It's probably easier to understand, but that's the route. If I go back, it's kind of confusing. So Berlin is on the left, Hamburg is on the right. And if you compare it with this one, yeah, you can see it's the right data. So after we got the coordinates and transformed it into the XY plane, we then approximated it with a spline. That's just a subset of the data I just showed you. And the approximation is the spline. It's just XY shown here. And we did all the same for XZ as well. Okay. And I already talked about the normal forces, which are dependent on the velocity and the radius. And you can see the formula below, but we want to know the radius of the route at a given point. So this is just an example where we approximated a point on the spline with a circle, so we can get the radius of the function, or the spline, basically. Yeah. With that, we can start optimizing. And what we did, or what I did, is give it a profile where we accelerate quite high at the beginning to the maximum velocity, which is 280 meters per second here, and then having a constant speed, constant acceleration being 0, and then braking at the end. And with optimizing, I'm using SciPy, but I'm giving it a couple of starting points where I distort the trapeze profile a little bit. So you can see the distortion in the data probably. I hope it's enough DPI, but yeah, so we are handing over quite some acceleration profiles to SciPy, and then let SciPy optimize every single one as a starting point. And yeah, to these starting profiles, we have these velocity profiles as well. You can see the constraint that V at the end is not fulfilled. It's the route length below, so that's over the whole route. But SciPy can change the acceleration profile in a way that's that V at the end, or velocity at the end, is 0. So that's not a problem. So I'm just going to show you some optimization results. As I mentioned, I'm not finished, but they're probably already quite nice to look at. So we had 4 acceleration profiles, or 4 starting points, and now we have 4 finished optimizations. As you can see, we have the upper and lower constraint on the acceleration at 6 meters per squared second, but at no point of these is at 6, so the comfort is too low for the passenger, so that the travel time improvement is worth it. And now I'm going to show you the velocity. As you can see, the second profile, the orange line, is quite fast, but as shown in the next plot, is not valid. that's another reason why we iterate over a couple of starting points, because some of them don't get valid, or yeah, just don't work. Let me. Okay, so, and I'm going to show you why the second profile is not valid. This is the normal acceleration, and you can see the second profile is all over the place, meaning it doesn't fulfill the constraint on the normal acceleration being below 2 meters per squared second. The third and fourth profile do. So I basically picked the ones that are within the constraints and work pretty well. Yeah, so it's kind of brute forcing, but it's better than nothing. And the result I got here, with not many iterations, is that the Hyperloop would need 60 minutes for the route from Berlin to Hamburg, or Hamburg-Berlin, and the ICE in comparison 103 minutes. That's not that much faster, but it's not the optimal combination of travel time and comfort in the objective function. So if I lower the weight for the comfort in the objective function, the result is going to be much faster, but we are still trying to find good weights for these the parts of the objective function. And then I'm already coming to possible improvements. So I constrained the problem at a normal force of 2 meters per squared second, which is quite low. If you think about sitting passenger, this can be can be higher. So if a higher normal force is given, the travel time will be faster. And I need to re-evaluate the comfort metric, because currently the comfort is computed as the average of a sum of the jerk, so the change in acceleration values, and then the acceleration plus the normal acceleration. But this doesn't work as that good right now, so I'm going to look into that. And we can, or this optimization is without cant. So as you might know, most of the trains drive on an angle, basically, to reduce the normal forces for the passenger. And this reduces the normal forces as well, resulting in a faster or a lower travel time. And probably for good comparison, the Deutsche Bahn has a normal force of, or it is allowed of 1 meters per squared second. So yeah, 2 is not that high, considering that you can still go to the toilet, walk around and everything. So yeah, that's it. Probably you already know that slide, but thank you very much for your attention. And if you have any questions, feel free to ask me.
Thank you, Justus. I think the first question is already on Slido.
Okay.
And it is, would you have an estimate how much the solution would cost to construct for the mentioned distance?
Wait, I couldn't understand it right now. I'm just gonna, can I open the link on my phone?
Oh, you should. Like, the password is already in the chat.
Okay, give me a second.
Otherwise, I can just say it again if that helps.
I think it's the easiest. So if I just look at it, shouldn't take too long. Wait. Back transport seminar. All right. Okay, so now I don't have that information. Because we are just looking at the potential of the the travel time, and not at the costs that would, yeah. No, I don't have it. Sorry. Okay, and I see a question about did you look into the increase of energy consumption for the new velocity profile? So as the energy consumption is not modeled yet, it's not taken into account, but I'm gonna, like, as it's modeled properly, we will take it into account and then find a good solution that fulfills comfort, energy consumption, and the travel time. Then the question is, did you think already about how to use the routes to build Hyperloop infrastructure, like on top of rails or below? I think there are a couple of approaches. We thought about on top, like on not so in a way that the train or the trains could still drive there and just build a tube above, but that probably results in problems with tunnels or bridges. So I think Nevomo thinks about integrating Hyperloop technology right into the track. So that's a possibility too. But our basic idea was to build it next to it or above it. Yeah, that's why we have a small smoothing factor in our spline. So it might differ quite little from the original track, but it's so small it's not really relevant. Yeah. Is the distance between Hamburg and Berlin maybe too short to be used for a Hyperloop? It probably is, but as we saw that the normal forces were constraining the travel time. So if we have a longer route, this could still be the same problem, because we basically need a straight track for low normal forces. This could be the problem for every track that's built. I mean, these tracks were not designed for high speeds, or not as high as a Hyperloop could go. The route from Hamburg to Berlin has some parts where I think the upper speed or the high speed limit is 230 or 250 kilometers per hour. And yeah, Hyperloops are above it. So yeah, that's probably just a regular problem. But it's an old route. We probably should look into Berlin Munich. That's quite new and more straight than the one from Hamburg to Berlin. Yeah. And then someone asked, did you also look at highways? Are they better for Hyperloops than railways? We didn't look at highways so far, because our assumption is that railways are better suited for high speeds. But with our code setup, it's quite easy to look at highway routes as well, because we just need to provide the start node and end node of the Autobahn, for example, and then we get the full route and we can optimize over it. But we're going to look into it, but we assume it's not going to be better than using railway roads. Okay. I think that's it.
Exactly, yes, I would also say those have been all questions. Thank you very much, Justus, for
Thank you.
your contribution and your support to the seminar. Thank you very much. And now we would like to hand over to Elias from TUM Hyperloop to introduce our next speaker and give a short insight. Thank you very much.
Cool. Hello, everyone. I'm happy to introduce Joris today, who's our second speaker of the seminar. So Joris has been part of TUM Hyperloop for almost 2 years now. He's been part of the tube team here as a civil engineer, and he's been investigating on topics like concrete testing, tube material, and also the vacuum system. And in this area, he was also writing his bachelor thesis, which he's going to talk about right now. And yeah, I'm excited for the topic. It's pretty cool to have him on the team. He's been a strong team member, giving us some input, not only for our current topic, our current project demonstrator, but also for the future with his research. So cool to have you here. I'm excited for the talk. And over to you, Joris.
Yes, thanks a lot, Elias, for the introduction. Thanks to you as well, Justus. I think it was a great presentation, and you can look forward to the evaluation, the results of your thesis with confidence, I think. Am I visible, audible? Okay, good stuff. All right, thanks a lot again for having me. Today I want to discuss permeability measurements on concrete for Hyperloop tubes. This is a topic I have been working on for 1.5 years, I think, right now, and I've recently also written my bachelor's thesis about, of which the title is Permeability Measurements on High Performance and Ultra High Performance Concrete for Hyperloop Tubes using Helium leak detection. So quite a lot. I've written this thesis at the TUM School of Design and Engineering at the chair of construction. So I come from a civil engineering background. I would suggest we dive right into it. Firstly, I want to discuss the problem of permeability a bit, then talk about helium leak detection, which we've used, show some series of experiments we've done, and then finally draw a conclusion from it. So as you might know, the TUM Hyperloop program is currently designing and building a passenger-sized Hyperloop demonstrator, of which the exterior shell, so the tube, will be made out of concrete. And I think you're probably also aware that concrete is a porous material, which means that particles from the outside could potentially move through the shell into your system. And if this flow becomes too large or too big, it could destroy your vacuum. And so you need to adapt your vacuum system to that a bit. And this is what we refer to as leakage. And for us, it was very important to quantify this permeability of concrete. And for those who do not come from a civil engineering background, usually we define concrete into compressive strength classes. And this is always a C followed by 2 numbers. So for example, here a C50-60 means a concrete with a cylindrical compressive strength of 50 megapascals and a cubic compressive strength of 60 megapascals. And the scale goes up to high performance concrete, and then from C100, 150 onwards, it's referred to as ultra high performance concrete. And these last 2 categories of concrete are quite new, and they have a very high density, very high strength, and also very low porosity. So they are actually very well suited for Hyperloop application. The usual way of detecting permeation of concrete or permeability of concrete is the so-called sample hole method. According to the literature, this, however, did not really deliver reliable results for the HPC and UHPC concrete types. So we had to come up with another solution. And the solution was called helium leak detection. This is a method that is very common in other industries already for detecting smaller leaks. And with it, you're also able to quantify the total permeability of a concrete specimen and then extrapolate that to longer distances. Some basics maybe. So what a leak detector does, it determines a leak rate. This is defined as the change of pressure in a given volume over a certain time with the unit millibar liter per second. And we use helium as a tracer gas because it's a very safe gas. It doesn't really react chemically or physically. It's environmentally compatible, and it also has a very low content in air of about 5 ppm, which means that you can really detect even the smallest of leaks. And the way we applied it was as follows. So we built a test stand ourselves with, here in the center, a concrete specimen clamped into a steel frame on both sides via 2 layers of O-rings. You can see the O-rings here going around, and thus creating 2 vacuum chambers on each side. One bigger one here in the center that is used to pressurize the helium to your plate, and a smaller one in between the O-rings to prevent helium from leaking out of your system. This could lead to an increased background rate in your testing chamber. And the leakage detector calibrates to this background rate. And if then you detect a rise in the leakage rate, you're not really sure if it's from permeation or if it's just because the helium leaked out of it. So it needs to be really airtight. The other reason for it is the fact that we don't want air from the outside moving into our vacuum, because that changes the sensibility of the measurements as well. And then, to start a measurement, you basically switch on the leakage detector here on the testing side, marked with T. It pumps down the gas from the large vacuum chamber, or the air from the large vacuum chamber. And you do the exact same thing with your EcoDry Plus vacuum pump here on the left side, on the gassing side. At the same time, you're having this vacuum running between the O-rings during the entirety of the measurement, of course. And then as soon as you've reached end pressure on the gassing side, you can close this valve here, open the valve that applies the helium to the concrete specimen, and you do this at atmospheric pressure. And then because there is a pressure difference, the helium will start permeating through the pore space of the plate and will be detected on the other side by the leakage detector. That's the basic principle. And you can actually quite well compare this to a sponge that you fill up with water. After some time, the sponge will be saturated, and there will be a continuous flow out of water of the sponge. And the same happens with your concrete plate as well. You apply the helium to it, the pore spaces will get filled, and there will be a continuous flow out. And this flow we refer to as maximum permeation. And here, for example, on the right-hand side, an exemplary permeation curve. So at the start, it rises quite quickly. And then after a certain time, this curve should flatten, and this red dot is the so-called maximum permeation. And now if you would say, okay, this maximum permeation on our 30 by 30 centimeter test plate is 10 to the power of minus 4 millibar liters per second. And we would now like to extrapolate this length, this leakage to a tunnel of 2 kilometers and with a diameter of 3 meters, for example. This would lead to a leakage rate of the tunnel of 20 millibar liters per second. And if we have an operating pressure of 0.1 millibar, this is just an example, you would need a constant pumping capacity of 750 cubic per hour. You need to have a vacuum system that's really able to pump down this volume at all times. Now, as we've already seen, of course, with rising area, the permeation also rises. This is because there's simply way more contact points. On the other hand, of course, with increasing shell thickness, the permeation decreases. This was not really confirmed in our tests. For example, if we take a look at the UHPC1 series on ultra high performance concrete here on the right-hand side, and you see plate 1 and plate 2 have the same thickness, 5 centimeters, but a different leak rate. And this is mainly due to manufacturing errors. These plates were all steel fiber reinforced. And in the case of plate 2, the steel fiber reinforcement led to a big hole on the surface without concrete coverage. And due to this big hole, of course, the helium can move in easily and from there on move into other pore spaces. And this leads to we however did use this proportionality ratio to calculate up to a 20 centimeter thickness plate, because this is from our point of view a quite typical shell thickness for a concrete type of tube. And as you can see here for the tested concretes, so an HPC and 2 UHPCs, the maximum permeation is all in the range 10 to the power -5 millibar. And this is really much lower than we initially expected. So quite some good results. If we would again then take this leakage rate, for example, now for UHPC1, the real leakage rate we've measured, and then extrapolate this to a track of 600 kilometers, so roughly Munich, Berlin, at an operating pressure of 1 millibar with a radius of 2.1 meters and this shell thickness of 20 centimeters, we would need a pumping capacity of 14,000 cubic meters per hour. And this can be provided by 12 dry vac pumps of this type or 23 social vac pumps of this type. These are pumps from Libel, just as an example, but as you can see from the power consumption already, there's nothing for such a long track. So this leads to the conclusion that the concrete leakage is not going to be a big deal if we are able to manufacture the tubes in a good way, so without cracks. Probably the biggest challenge is going to be to pump down these large volumes in an acceptable time with as little pumps as possible. And to pump down 600 kilometers of tube, you would probably need like hundreds of pumps to do this in an acceptable time. And of these hundreds of pumps, you would then only need 25 pumps to pump down your pump. So again, this leads to the conclusion, 10 to the power of -5 millibar liters per second for the tested high performance and ultra high performance concretes, way lower than expected. This means that concrete permeability itself plays a subordinate role in the design of a vacuum system. It offers potential for optimization. You could think of maybe having smaller radii. That would lead to less material consumption, of course, and cementitious materials are responsible for quite some carbon emissions, so it's something to think about. This also leads to less leakage, but of course means that that's something we want to have. Then maybe smaller shell thickness is a thing we could think about. This also leads to less material consumption at the same capacity. It of course leads to higher concrete leakage, but this might be acceptable since it's so low. Of course, it needs to be structural. We probably can never have 5 centimeter thick shells because we need to have reinforcement in the shells. We need to have retentioning systems in the shells. And yeah, that's probably never going to be an option. But maybe having 15 centimeters would be a point of discussion. Then future research should expand this data set. Maybe I can go some slides back here. 7 successful tests in a period of 1 year of testing is not that much. And this is due to the fact that the measurements just took really long. Some measurements took weeks. We tried to use an overpressure as they use in the semi-hole method I discussed in my introduction as well. They use an overpressure of 1.5 to 3.5 bars, and with that you're able to force the specimen to a result faster. We were unfortunately not able to do it with our mechanics because we had some glued connections in there, and so we need to make it more robust to have more testing in the future. And most importantly, lastly, of course, is going to be the demonstrator, because with the demonstrator we can really determine the total leakage of the system, including the segment joints. We are never going to have a monolithic 600 kilometer tube from Munich to Berlin. This tube will always be built out of various segments that will be stick together and will be connected via joint feeding. And we can expect some leakages there, and maybe these leakages are higher than the concrete. So that's definitely something I'm very much looking forward to be working on in the team. For now, I would like to thank you for paying attention. if you wish to have a copy of my thesis or have any questions, feel free to write me an email. And yeah, I'm also open to answer questions online. So thanks a lot.
Great. Thank you very much. Nice talk, nice insights. Good that you're on time because we have quite a few questions on the topic. Seems to be pretty interesting for the crowd, for the people. Let me start. How do you spot a leakage without a helium leakage detector? For example, during running the facility and vacuum, which techniques have you looked into?
This is something I cannot answer right now. The thing is, if everything is constructed the way it should be, then not going to be a problem at all. But as soon as we have a crack somewhere, your vacuum can be destroyed pretty easily, pretty quickly. That's definitely a thing we are looking at the moment. You can do this with ultrasound systems. That's something we are looking at. I think heat is an option as well, but this is something for the building phase. So I really can't answer too much in detail on that yet, but it's important to look at because during the construction phase there can always be minor accidents and cracks, and then we should really be able to find the leak. Otherwise, the system just doesn't work.
Yeah, cool. Thanks. And what permeability range are you targeting for future track?
Yeah, depends on the pumping system. I mean, as I said, the biggest challenge is going to be pumping down in an acceptable time to operating pressure. So let's say from 1,000 millibars to 1 millibar. And let's say we want to do this in 48 hours. Then we need quite a lot of pumps. And if we already have these pumps, we could also maybe accept a higher leakage rate. But of course, over the course of 50 years, it might not be as economically feasible or environmentally possible to have so many pumps running all the time. So the leakage should be as low as possible, of course. But as I've said, maybe changing the geometry a bit could be an idea. Having slightly thinner shells, therefore using way less material, might be a possibility, and then having a bit more pumps run. I cannot give you a number right now of what the ideal leakage rate would be.
Yeah, but to sum up, you're not concerned about the leakage during operation, more like the time to initially set it up. Will be the problem.
Yeah, if there's no construction errors, then the leakage should not play.
All right, thanks. What strategy do you have to make concrete more permeable? Have you looked into solutions there? Is that possible?
More permeable? Maybe could you explain the question a bit more, because I would actually like to
maybe.
have this.
I think the question was meant the other way around, actually, to make it more to make it less permeable.
Okay. Yeah, there's a lot of research on this. As I've said, these high performance and ultra high performance concretes are quite new, and they have very low porosity. And with the right pulse treatment, it's in some cases also possible to stop the interconnectedness of these pores. And if the pores aren't connected anymore, then you can really call the material completely airtight. But these concretes are also very expensive. So if we need lots of material, it would also be a very expensive material. So I think you need to find a right break-even point there between costs and airtightness. Yeah.
Okay. Quick follow-up question. Is there some sort of cover that you can use inside of the tube to make it more leakage proof? Is that a thing?
I don't know if it's possible for air. It is possible for water. Of course, in concrete, in concrete technology, there's quite a lot of research going on permeability as well, because, for example, for bridge or road construction, there is de-icing salt and stuff, and you don't want to have these salts permeating into your concrete body, because it could then lead to corrosion and lead to failure of it in the end. And there they often use like a hydrophobic coating that you apply to your concrete body, and this would make it hydrophobic, so water and other particles could not enter. I don't know if this is possible for air. You would probably just need like a real sealing, and I don't know if such a thing.
Okay.
It probably exists, but
no problem. Thanks. Have you got any long-time data on permeability? Maybe both in terms of how the leakage rate develops over time, and also how the material develops over time?
Yeah, this was very different. Some measurements took a couple of days and reached their static this endpoint, this maximum permeation point, quite quickly. Some concretes took a lot of time. I think it was mainly due to our test stand, which was far from perfect. It's very hard to get it really airtight. And there were also some concretes that had like a post-treatment layer. And I think this also played a role for the helium. Somehow it blocked the gas a little, and there it took a bit longer. Yeah, I mean, I'm happy to send some permeation curves. You can take a look at it yourself. Some I still do not really understand. Normally, it should look like the permeation curve I've shown in my PowerPoint presentation. So at the start, yeah, nothing should really happen. Then after some time, it should rise pretty quickly and flatten completely. But this was not always the case.
Okay, we also have some general questions about the concrete construction itself. So how do the concrete types withstand weather effects, cold, heat, water, diffusion?
Good question. Yeah, it's a thing I'm not really an expert on. I mean, concrete is a shrinking and creeping material. And yeah, if we have if the concrete creeps and shrinks, of course there will be movements, and this will lead to tension in the system, and that could also mean that there will be openings or cracks, and that's something we really want to prevent. For now, for the demonstrator, this will probably not play such a big role, but it's definitely a thing we need to take a good look at when we have our demonstrator, and like maybe it will be some years before we see a real result there. But yeah, for serviceability and durability, this is definitely a very important topic. Also because these concretes we are using right now have quite a high cement content, so way higher than your normal residential concrete, your residential building concrete. And cement is actually the material in the concrete that is responsible for it. So it's something we need to look at.
Yeah, but cool. I'm also excited for the data that we get in the future. Thanks. Another general question. What is your timeline for concrete construction for the tracks? Do you know something about that, or is it too far away from the topic?
Like for a real track? Well, I don't know. I think this is probably something you could quite easily not easily manufacture, but as soon as it's there, you can quite easily stick the segments together and then make longer tracks. But I really cannot give a number.
Yeah, the process itself is more or less.
Yeah, we're not going
scalable.
to build. You're never going to build this on site. This will always be delivered from a factory and then brought on site, and then you stick it together. So yeah. And if you're able to work quite fast in the factory, and you can manufacture the tube segments quite quickly and drive them to the construction site and stick them together, you can build such a system pretty quickly, just like a prefab house.
Yeah. Oh, cool. And another general question, maybe you can answer that with your gut feeling, rather. It says, do you see concrete as a long-term solution for Hyperloop? Do you have a feeling, impression there?
I really cannot say anything about this. I mean, I think for us at TUM Hyperloop, it's really, for me, for example, it's really cool that we get to work with concrete. And from a civil engineering perspective, it is definitely something that is very challenging and something to look at. Also from a cost point of view, it is definitely better than steel. But of course, as long as we are not able to have a CO2 neutral cement, this leaves quite a big carbon footprint. And that's definitely something we need to look at, because I think all Hyperloop teams sort of have this promise of climate neutrality. And yeah, again, if we use a lot of cement, I don't see how we can hold this argument if we're going to build long tracks. But this can change in 10 to 15 years, maybe. It is possible to have climate neutral cement. From a structural point of view, it's really not my expertise. I've been doing a lot of concrete testing, a lot of permeability testing, but I'm not really into comparisons with steel yet. I haven't worked with steel as a material, so I really don't know.
Yeah, fair enough. Thanks for the insights there. And the last question, also quite nice. Is the pieces openly accessible? The topic is highly interesting.
Yeah, I have to discuss this with the chair. There is some stuff I probably need to blacken out, some concrete recipes, because they're confidential. But I think if we do that, we can definitely send it around. Not a problem.
Yeah, that will. So if you're interested in that, follow yours on LinkedIn or whatever, and then can send you maybe some paper one day.
Yeah.
Cool. I think we're good in time. Thanks, yours, for the discussion. It was great talking to you. Thanks for the insights and the explanations. With that, back to Natalie, I guess.
Thank you very much, Elias. So thank you again very much to Justus Wolf from Missouri Hyperloop and to Joris Barenze from TUM Hyperloop for your interesting talks tonight. It was really nice to learn about what you're working on and your theses in your Hyperloop teams. And also thank you very much to the audience for the participation in the questions. And of course, as always, also a big thank you to the organizers, to Eurotube, Missouri Hyperloop, TUM Hyperloop, and the University of Applied Science in Leer, as well as our part from Swissloop. So in that sense, we wish you a good week. We have our next seminar in a week at the same time at 6 p.m. And there again, we will have 2 talks, one from the side of Swissloop and one from the side of the University of Applied Science in Leer. Until then, we wish you a great week. Enjoy the springtime and see you soon. See you in a week. Have a good week, everyone. Goodbye.
Thanks again.
Bye-bye.
Bye bye. Goodbye.
Bye.
Thanks for the talks.
Bye. Thank you.